Are you ready? So this is today's lesson. It is mainly the consolidation of considering the effect of the concentration and the pressure on the position of the equilibrium system. So because in the past 2 days we have got a very quick overview of all those, right? So it's time to have a consolidation and how would you get approach to the problem. So first of all, by prediction, okay, by prediction we have got a saying. We call it we call it as a Lechatier's principle. What is that? It tells you a prediction on that we have got a change applied on the equilibrium system. There will be a shifting in equilibrium position so as to what? Reduce the change, okay? Reduce the impact. So let me wait for you. So what is meant by that? To reduce the change, right? So you're going to do the equilibrium shifting. So this one is a very it is a useful tool for you to get to know how the shifting in equilibrium position can be made. Okay, so this is what I just talked about to all of you these 2 days before. Okay, and in between, of course, we need to deal with some calculations, and as well as we need to consider the 2 cases on the concentration. Now, first of all, concentration of the substances has been increased, so the equilibrium position will shift to the opposite side. Okay, according to Lechatier's principle. Okay, so reduce the concentration of these substances. So which will affect the the extent of the change of the forward rate and backward rate. Okay, so what is the underlying principle is that you are going to alter. You're going to change whether it is the forward rate or backward rate upon the change, such that it will cause a shifting in equilibrium position. Okay, and this is the saying about that concentration. Now, it's easy, right? How about pressure? Pressure is a little bit complicated. You need to consider what? You need to consider the number of moles of reactant and the number of moles of product at either side, and such that you can judge whether or not the equilibrium position will be shifted to the left or to the right, or even no change. Okay, so this is a little bit more complicated. So remember, for these cases, you are going to take a look on the equation. Okay, how about this? How about a change in concentration? The change in concentration, if you increase the concentration of reactant, the target way is to decrease the concentration of reactant. So the equilibrium system should be shifted to the right. So okay, by decreasing the concentration of reactant, you know that do it in reverse. Increasing concentration of product, you're going to do it on the reactant side, while you're decreasing the concentration of product, you are going to the right-hand side. So what are they in common is that the Kc value doesn't change, no change, okay? So it is, remember, Kc, it is a temperature-dependent constant. It is temperature dependent, okay? So similarly, how about this one? The Kc value also doesn't change, okay? As said before, Kc is a temperature dependent constant. So the question comes, some of you may have got difficulty in managing the questions yesterday. I just, last night, right after the lesson, a student come to me and messaged me and said, Mr. Chin, isn't it that there is a shifting in equilibrium position, which means the Kc, the value of Kc will be changed. So why doesn't it be changed? So indeed, Kc is the temperature dependent constant. So nothing is related to the concentration or the pressure of the equilibrium system. So what is Kc? Now, I would like to give you this equation indeed tonight, but this time I would like to show you what is Kc. So what is that Kc? How is it related to temperature? Now, Kc is related to the temperature like this, minus delta H over RT. Well, delta H is the extent of the reaction. So T is a temperature in absolute temperature, while Kc it is the value of the equilibrium constant. So you may see that these two they have got a relationship. What is that? We call that PV and RT, that R, the same R. It is the universal gas constant. So I do hope by doing so, somebody will get to know that, well, it is nothing related to the change in concentration or the pressure of a system, which will affect the Kc. So remember, shifting in equilibrium position is one thing, while the change in Kc is another thing. In case there is a change in equilibrium position, that doesn't mean it's due to the change in Kc. It can be the case that the Kc value doesn't change, but the equilibrium position has got a shift. Okay, so I've just explained well why. Now, because of the you have already made a disturbance. So for the concentration, take a look on that concentration before we check the answers. Because somebody asked this, and I would like to clarify this with you here, first of all. Now, we call the memory about the concentration change. This is the one, right? You may see that, right? And a shifting in equilibrium position, it seems like having a seesaw, right? So at this time, I add something more on the reactant. So you may see that on the green one, and then the green ball, I add something here, and then the equilibrium system will adjust itself by shifting towards more on the right-hand side. So by doing so, we will until the forward rate equals backward rate. So we will call that a dynamic equilibrium has been attained. So what will happen is about that too. Now, the equilibrium position have been shifted. Why? Because we will want to take a look on the relative, okay? It's on the relative amount of this. Can you see that? This one, this is 2, 2, and then 3, and this one is not equilibrium, while this one, can you see that? Right? It is just 3, 1, 4. So what is mean by that? The seesaw hasn't been changed, which means that the Kc no change. However, because of the disturbance has been made, I have added the green ball already. Okay, so the whole equilibrium has been disrupted. So the corresponding number of the reactant and the product respectively will change, will adjust itself, such that they will get that balance again. So can you get my point? So when you compare with the original case, which is 3, here now is 4, we will take a look on the product side, which means that the equilibrium has been shifted. Okay, have been shifted towards the right-hand side. Can you get the point? So by doing so, we would call this type of a case Kc no change, but we have got a shifting in equilibrium position. Remember, okay? Do you get my point? So once again, once there is a shift in equilibrium position, that doesn't mean Kc has been changed. It's just the minor adjustment by the system itself. Okay. So the ultimate goal is to keep to keep this one, that unstable situation, back to this. So what is that unstable situation? Now we need to use mathematical expression on telling this. It's not Kc. What is that? If you understand it by using mathematics, you may think it like this way. You use what? You don't understand? Anyone who can help? One way, tell me. What is that equilibrium? Is it equilibrium in the middle? No. So What is the mathematical expression to tell this unbalanced situation? What is that? What is that? Any expression about this? Now, we have got another way to, I give you one more hint, right? So you may refer to the case on here, 40.5. 40.5. So what is that? It's QC, right? It's QC. You may also use QC and try to relate to KC for you to predict the shifting in equilibrium position. So this is what I would like to give you as a summary here, right? So you need to take a look on the QC and KC value to figure out whether there is a shifting in equilibrium position. If there is, where to where? Can you get a point? So the dynamic equilibrium, of course, it refers to the case that QC equals KC. Well, if QC is no longer equal to KC, just like this one is with molar either smaller than or greater than KC, so what will happen? There will be shifting equilibrium position respectively. One towards the right, the other one towards the left. Do you understand? So, which means that the shifting in equilibrium position can be predicted by two ways. One is Le Chatelet's principle. So in case I do something to increase the concentration of reactant, the equilibrium system will be shifted in response to it, such as to reduce the impact, which means to reduce the increase in concentration of the reactant. Okay, so that's why you will be shifted to the right. If you take a look on this case, what is that? I increase something on the reactant side, which means this case, right? The QC is smaller than KC. So your equilibrium system will also be shifted to the right-hand side. Can you get the point? Anyone who can get what I mean, could you please put a tick here? Yes, to have got two ways to explain, right? One for you to predict. One is by Le Chatelet's principle. The other one is what? Is by using QC. Yeah. 有李振傑、余子豪、魏卓賢、徐家榮、余一斌。How about you? Do you understand? 魏卓賢。Double Cyrus. You don't understand. How about李振傑?李振傑, you what is your doubts? Tell me. I just saw you putting across here. That you may turn on the mic and ask. No. So far, no. How about the others? Now, how about the second case, the pressure? Can you use, now last night I asked you guys to leave you a question, right? Any alternative method for you to predict or the effect of the pressure change on the shifting in the equilibrium position? I asked you guys to think about this, right? Last night. So anyone who can tell? What are the possible methods? 温志偉
by predict the result by the mole ratio of the reactant side and the product side. When the reactant side total molar is more than product side, the reactant, the equilibrium shift to right. Inversely, when the molar product side is smaller.
Mm-hmm. Mm-hmm.
And when
Yes, that's, oh, you're referring to this table, right? The concept is very similar to this table. So what is the relationship between this? What is the relationship between number of moles of the gases and pressure? Okay, you know, it is a positive relationship. So you may use this one to predict. You may use this one to predict in your in the case, right? So because of that, last night we have come up with so many exercises, so many explanations using this type of concept, right? Any other method besides this? Can you suggest another method? Samson, do you know? Besides using this one, any other method? Samson, 你同 No idea. How about Wu Galong? Are you here? Not here. Oh, some of you absent today. Are here. Wu Galong here. Wu Galong, can you give another method for you to? Yes. Yes, that's right. Can you elaborate more on QC and KC? You use this one to relate. Now, because this one is too generalized, right? I would the better way is to show you the three scenario. Yes, last night. Take a look on this. The first case, this one, N2O4, NO2. Can you use QC for the others? Can you write down the QC value on this? QC and KC for this. Use this to compare. Now, this one is a blank, so I would like to have this, right? QC and KC. Now, for the equilibrium system, it is N2O4 gas to form, let me put it this way. I'll put it in the right box, okay? So we have got three cases, and the book has shown you the three cases, right? The three cases, cases 1, 2, and 3 for the scenario. Now I would like to show you this one, different cases. Case number 1, okay? Case number 2, and case number 3. So case number 1 refer to N2O4, right? It is what? The more products than reactant in the equation, as shown in the equation. The other one, the second one is reverse. There will be more product, normals of gases at reactant side. The third case, it is the mole of gases at reactant side and product side are equal. You will be given the three cases, okay? The three equations. So let us try to have a summary on what is that. I try to make a comparison of these. This time I use the QC value to judge. Can you get my point? Now we have got that one. Now I would like to show you the three equations. The first one, it is N2. The first one is N2O4 gas to form 2NO2. Okay? So the second case I would like to show you is on the what? Two cases, right? Increased pressure and decreased pressure. So altogether the box will be this, right? Very similar to this. Increased pressure, decreased pressure. Can you get what I'm going to do? You get it? Now Samson try. So we have got two cases, two scenarios. The first one is increase in pressure. The other one is decrease in pressure. So how does it affect the shifting equilibrium position? So for this one, increased pressure, can you relate something about this? So first of all, how can we make the pressure increase or decrease, Mr. Chin? How? How? Yes, volume. The increase or decrease? Tell me, is it increase or decrease? Decrease, yes, that's right. So this is what you need to know, right? It by decreasing the volume, okay? By the increasing the volume. So can you get my point? So first of all, you need to get the scenario. By decreasing the volume of the fluid mixture, this one is by increasing volume. So why do I need to write down volume? Volume, okay? So it's because you need to do the mathematical calculations involving concentration. So anyway, you have to deal with volume. Can you get a point? Now, so first of all, QC, what is mean by QC? QC for this case, it is the NO2 gases at that point square over N2O4 gas. Can you get a point? So what's next is to change, is to define the molarity. How will you get the molarity? The molarity of it is the number of moles of NO2 square over V2 square over and number of moles of N2O4 over volume. Can you get my point? Can you get what I'm going to do? You get it? So what's next is to cancel out the volume term. So what will you get? How many volume? V to the power 1 or V to the power minus 1? What is that? In reality. How about volume? Do you know how to cancel out? You know how to cancel out the term, right? Cancel out, and what's next? What is that? 1 over V or V? 1 over V or V? 1 over V, is it? Yes, V, 1 over V, right? This one. 1 over V times, right? Can you get my point? So afterwards, it is a very powerful way for you to judge. Increase the pressure by decreasing volume. What is happening to the QC? Can you judge? Now, if V here, we have got a decrease in value. Can you see that? Decrease. So what happened to the whole data? The QC value will become, is it equal to KC again? No. Increase. Yes, that's right. So which is greater than, equal to, or smaller than QC? What will they change? Lei Tong, could you please elaborate on this? How does it relate to KC? Greater than. Yeah, greater than. So in order to go back QC to KC, so the QC should drop. So the equilibrium position should be what? Can you get my way to do? In order to restore QC back to KC, the QC should drop until QC equals to KC, right? The equilibrium position should be shifted to where? To drop. How? How can I make the whole data drop? It's too big, right? So I try to decrease this one and I increase this one, right? Yes, that's right, to the left. Can you get my point? Decrease in NO2, increase in N2O4, which means shifted to the left. Do you understand? Anyone who understand what I'm going to say? Could you please put a thumbs up? First of all, you get to know what our way to do. First of all, you understand? You understand? Yeah, good. So could you please try to finish the remaining? Now, how about increase in pressure, decrease in pressure? I do it in reverse, right? QC becomes what? Again, I will use this data. I can skip it by writing this. It is QC value, what will happen? The volume will increase, right? Which make that QC value smaller than KC, okay? Smaller than KC. Can you get my point? So what is the, what I'm going to do to say it again, to restore QC to KC, the KC will increase until QC equals to KC, which means equilibrium, right? You want to attain back to the new equilibrium position. So the equilibrium position will be shifted to what? Right-hand side this time, by having a net forward reaction. How about this one? In reverse, it is a net backward reaction. Can you get my point? So this case, how would you think it of this way? Increase in concentration. QC value will have got increase, right? So which means that QC, you are going to suppress, you increase the QC value, right? This time, increase the QC value. How? This one is more, this one is less. And the equilibrium position, I say that is shifted to the right-hand side. Understand? Can you get a point? Now, once you know it, and you may do something similar to the question 2. Question 2, what is the case? More moles of gases in the reactant side. The case on the book, it is on 2, right in thicker lines, 2 SO2 gases plus O2 gas to form 2 SO3 gas. The third case I would like to show you here, it is hydrogen iodine to form hydrogen iodide, this one, according to the book, right? So you may find that. Can all of you figure out the remaining part here? For those who can manage, for those you think that you can manage, now could you please put up a hand? For those who can't, let me know as well. You know how to manage. If you know how to manage, put a tick. Don't know, cross. Or you put up hand. Yeah, that's right. Huh? It doesn't matter. You know. You don't know. I see some of you still cannot manage. Don't worry. Now I give you one more example here, right? Do it bit by bit here. How about this? QC, expression of QC. Similarly, just like what you are having on top, QC is equal to what? the concentration of SO3 gas square over SO2 gas square times concentration of O2. So you do something similar and you will get rid of those n volume terms, right? So you may get SO3 square over number of moles of SO2 square times number of moles of N2. So what is V? What is in terms of V? Is it V, 1 over V, or what? Now the volume terms of the square will be cancelled out. How about number of moles of NO2? It's number of moles of NO2 over volume. So 1 over volume, which means what? It is volume here. Can you get a point? Anyone who can get what I mean? Can you get what I mean? Why is it I write down just V here? You understand? You understand? Don't you don't understand? Yes, cancel out for volume terms. You know that molarity. What is calculated as molarity? Molarity equals to number of moles over volume. Okay, so the scenario, so you are going to do something like this. You're going to start from this. Okay? Yeah. So you are going to have a molarity here, number of moles of substances over volume. So that's why the volume will be here. So similarly, you know that QC here. So increase, the first case is decrease in volume. Decrease in volume makes QC what? When volume decrease, the QC here, the value will be smaller than KC. So can you get my point? So in this case, similar item, you do the same. QC equals volume times number of moles of SO3 square over number of moles of SO2 square times number of moles of N2. So you know that the volume, the increase here, the equilibrium reaction quotient will become greater than Kc. Can you see something different from the case above? Can you see that? Now the first case, increase in pressure, the QC will become greater than Kc. How about this one? It's smaller than Kc. How about this? For the case 1, a decrease in pressure will lead the QC smaller than Kc, while for this one, increase. Can you see the difference? So of course, what will happen is on the shifting in equilibrium position is different. So for the explanation part, I skip it. Very similar to one on top. So I would like you guys to give me a conclusion. What is a conclusion? Conclusion. The conclusion is that what? The equilibrium position will be shifted to where? To where? This part, it is right-hand side. This one, it is left-hand side. Can you see that? The same disturbance, but once I change the equation, the conclusion is different. Can you see the conclusion? How is the difference in the conclusion? This one, right-hand side, right? When you compare with this one, it's left-hand side. This one, it is right-hand side for the first case, when I decrease in pressure. How about second case? A decrease in pressure will lead to a shifting equilibrium position on the left-hand side this time. So you may solve it in terms of what? Mathematics. Can you see that? How is it so different? Can you get the point now? It's because of what? It's because of the order of the volume term Is it negative index or positive index? Can you get behind? If it's negative index, it seems like case 1. If it's positive index, it seems like case 2. Of course, the conclusion will be much different. You understand? How about the third case? Can you come up with a third case now? Third case, how about this? The QC is what? The QC is concentration of HI gas square over what? Concentration of hydrogen and concentration of IOD. So you do the same thing. You change it to number of moles and take out the volume terms, because the volume they are the same, right? You can cancel out. So what will happen if I take it out the concentration term, the volume terms? What will happen? How about volume? What's the order, the power of the volume for this case? Do you have any volume terms now? No, all cancel out already. All cancel out already. Can you see that? All cancel out. So no volume terms here. No volume terms. No. No volume terms. No volume terms. No molar volume terms. So can you get my point? So similarly, for this one QC, no matter if there's increase and decrease in pressure, it's the same, right? Which is a number of moles of HI square over number of moles of H2 times volume number of moles of I2. Okay, which means that the QC value only depend on what? The initial concentration, the particular constants, or the volume of the number of moles of reactant product, but not affected by the change in volume. Can you get my point? Not affected. Can you get this point? Not affected. So what is the conclusion in this case of both cases? Can you get my point? So it's easy spoken, right? So there will be no shifting. I do hope by doing this type of table would help you better understand the scenario. This time I use the QC value for you to judge. You may keep the screen here, right? You may keep the screen for further use. You better keep this, right? Because it is quite useful. Besides having the other table in the book, right? The one you use it by Leschetiz's principle. For this one, I use it as what? I use it as a type of a equilibrium constant here, right? So can you get it? Okay, you understand? Now, if you think that it will give you a better understanding, okay? Just clap your hands. No. Now, of course, somebody will think that Mr. Jin is just suitable for the people who are good at mathematics. Yes, you may think it like this way. Yes, it is another approach for those students who want to get to know more mathematical relationship. This one will help. If you don't understand using this explanation, don't worry. You will use Leschetiz's principle, and you may get the same prediction. Any questions? Any questions? Now, I know that you may need some time, right, to digest. Chen Junhei and Lu Xiu, have you watched the video? Have you watched that video before? We are no longer in a Qing dynasty, right? We are now in 2020. How about Zhu Gaming? 唉，老師話 what you have just said already told me whether or not you were present last night. Last night we just covered the change in concentration on the shifting in equilibrium position. How about the start of chapter 40? Have you watched it? The Monday one. How about the others? You feel better, right? Now, so if all of you would get to know what is that, shall we stop for this for a while, because this is very quantitative demand. You have got a great load of that. So for the remaining time, I would like you guys to take a look on the questions, MC questions as well as the long questions, to have a recap. Long question, please. MCs please this time. MCs here. MCs. Yeah, this is this one. The page 66. Take a look. Page 66. Question 2 to 7, as I've told you, up to 7. So take a look at question 2. Yes. So you got a nice well on the right hand side. So what is the hidden message? What's the hidden message? How does it relate? Somebody who just circled this right hand side, what does it mean by that? Now, first of all, check the what. What does it mean by right hand side? You check for the relative amount of reactant when you compare with the product. Okay, so right hand side, which means what? Product will be more. So product will be more, it is either B or D. Okay, can you get my point? However, you would say, somebody would say that it's D for sure, but not B. Why? The same value, isn't it, right? The data is the same. Yes, but the unit, check the unit. Check the unit, please. What is the unit? Now for this one, you may see the overall order, it is mole and then dm cube to the power 4, right? How about this one? It is mole per dm cube to the power 3. Remember that this one will be divided over this. So what is the overall unit? It is mole per dm cube minus 1 over 1, right? So this is the one. dm cube per mole. The answer is D. Can you get it? Like, you know, do you understand? Something about mathematics. How come it's 3? Order 3. It is 1 plus 2, right? Equals 3. And this one, 2 times 2 is equals 4. You understand? Good. How about number 3? Zhu Gaming, tell me. Show me your understanding. Question 3. Consider the following equilibrium system. Bromine water. Which of the following can turn the color of the system paler? So to start with, you have to get to know the color of those. Which one is color? Bromine is the only colored species. How about the others? All those they are colorless. 趙家明, where you? Yeah, tell me A, B, C, or D. Anyone who can help? 雍正南. Oh, D. Yes, that's right. 陳少明. Yes, that's right. D. Why? The adding NaOH, what will happen? NaOH, what will happen? How does it affect the equilibrium position? Yes, they will react with this. They will destroy some of the Na plus, right? It will make that decrease. So according to Le Chatelier's principle, they want to do something to reduce this impact. I want to make it increase again. How? They will be shifting in the equilibrium position to the right-hand side by carrying out a net forward reaction. Okay? Can you get my point? Can you get my point? So D is the answer. How about A, B, and C? What would be the answer for A, B, and C? If I choose A, B, and C, what will happen to the shifting in the equilibrium position? Yes, all three, they will have an equilibrium shift to the left-hand side. All three, they are the same, is it? Is it all three that are the same? First of all, increase in hydrogen ion concentration. So shifted to the left-hand side. How about B? Increase in both the concentration of hydrogen ion and bromide ion. Why is it ion but not is indeed a gas? How come Mr. Chin tell it as a ion? It's a molecule. How come it becomes an ion? Why? Tell me why. Why? Yes, that's right. So it dissolves in water, they would be ionized to form hydrogen ion and bromide ion. So this time, hydrogen ion increase. This one, hydrogen ion and bromide ion increase. How about the third case? I increase what? Bromide ion. Because this one, NaBr, solid, once it dissolves in water, it dissociates, right? To form, to liberate the aqueous bromide ion. So all those three, they are what in common? They are all in the product side. Okay, they are all in the product side. I wanted this over disturbance is to make the sum of the components in the product side increase in the concentration. So the equilibrium position will be shifted to the left, such as to reduce that change, according to Le Chatelier's principle. Understand? Now, one more thing I would like to address to all of you here is the constant is on the equilibrium constant. Now, this is I haven't told you in the previous video, right? So remember, so pay attention to this. Can you write down this one, the equilibrium constant on this? Kc is equal to what? Do you know? Can you write down the equilibrium expression? The equilibrium expression. What is that? What is the Kc? Do you know? Very strange asking, right? So you may find that it is HO8NaOBr AQ times hydrogen ion times bromide ion, okay, over what? Bromine water concentration. And what is that? Now somebody would love to write down this way, H2O get a liquid here. Okay, agree? Is it the one? To your understanding, what is meant by the molarity of water? What is meant by molarity of water? It is a constant. It is a constant at room temperature and pressure. What is the constant? It is about 55.6 mole per dm cube. Why is it? Why do I say it is a constant? In this case, water here, of course, it is a reactant, right? Because it is involved in a chemical equilibrium equation. But also, it is a solvent. So what is the hidden message? It is in large excess when you compare it with the reactant and product. So remember, this one is a constant. So how will you express the equilibrium constant? You have to skip the content of water here. So Mr. Jin, how come for the other cases, I remember I have written down molarity of water before. But how? But why does that time Mr. Jin did not cross out this one? Do you still remember? I have shown you some cases of having water to be embedded inside the calculations in the equilibrium constant. About this time, no water. No need to add concentration of water. Are you with me? Do you understand what I've just said? There's silence again. Can you locate the example? Where? Do you still remember the example? It is on chapter 39. If you remember, chapter 39, I've shown you this example before. Involving the concentration of water. Now, for example, this one's steam. Can you see that? Steam, question 19. Question 21, H2O. I've also included the concentration of steam. It's a matter of steam, yes, but one more case, even though I mark it as H2O liquid, you need not calculate. You have to calculate this time, but for the case in chapter 40, you need not calculate. A very special case. Can you show me which case? Yes, that's right. This is the one. Do you still remember? The question 27. Question 27. You are going to determine the equilibrium constant between the acid and alcohol to form ester and water. So in this equilibrium, you need to integrate water inside that as well in your calculations. Why? Why? It is now, it's not just H2O gas, right? It's H2O liquid. But how come H2O liquid you have to include into calculations? Lei Tong, do you know? It's a product. What else? Can you tell me the relative amount of this? Is it in large excess? Is it a solvent? No. Remember, okay? So can you get the logic? So under what situation would we get rid of the concentration of that species? It's not just whether or not it's a reactant or product, but also I try to check what? Is it in large excess? So solvent, of course, it should be in large excess. So you need not put them inside. Do you understand? And also for this case, the whole cases for acidification is not in aqueous medium. So the water here, the formation of water solely is come from the reaction itself, but not the solvent. So the concentration of water here is not a constant. Can you get my point? So that's why you need to calculate 0.0269 mole, right? For those who understand what I've just said, put a tick here. Tell me. You understand? You understand? You understand? Or maybe Layton has slept again. 徐家榮魏卓賢 you don't understand. Still here. All right. So do you understand? It is, remember, you are going to check the solvent, whether it's a solvent, in order to determine to cancel out. What are you going to do? How about other substance? What do you mean by that? You have to include, because in equilibrium calculations, you will experience a change. Now, of course, for the case here, right? Yuan has raised a very good question. How about this? Water, the amount of water will also be changed. How come Mr. Chin did not include this? Because it's solvent. Solvent will have originally a nearly infinite amount, right? A very large amount of water when you compare it with bromine, HOBr, hydrogen ion, and bromide ion. So even though there is a shifting in equilibrium position, either on the left-hand side or the right-hand side, it will lead to an increase or decrease in the number of moles of water, right? However, the original number of moles of water inside that as a solvent is quite large. So the change of those H2O, the change in water concentration is minimal. Okay, why? Because water here is a solvent. So we have got lots of water molecules here. So that's why I tell it as large excess. Can you get my point? So in response to the other substance, question about other substance, we need to integrate into it. The answer is absolute. You have to add it. You have to be aware of it. So the only case that you need to consider is water. If once you see water here, be alert. In case it is in case it also have an additional role of being a solvent, you better get rid of it, because this one is already the constant. But indeed, it's not just not putting it. Indeed, that constant here has already been embedded inside the KZ. Can you get my point? Such that we will say that it is still a constant, but not just but not disappear. It's not disappear, but it's just embedded inside the equilibrium constant. Do you understand? You get it now? How about question 4? Take a look. In which of the following chemical equilibrium system would the position of equilibrium not be affected by the pressure change? Not. Now, just like this case, what you need to check? Not be affected. Yes, that's right. Why? Yes, the mole. Can you elaborate more? I'll show you. On the left-hand side of the product side, they are having the same number of moles in the equation, right? So the volume doesn't play a role in affecting the value of QC, right? Just like the case, what I have just suggested in your whiteboard, this one, the third case, right? This is exactly talking about the third case. So the volume terms has all been cancelled out. So the knob will not affected by the change in the volume. So no shifting in equilibrium position, no change. Okay, the case number 3. Do you still remember this one? Yeah. So the answer is B. How about question 5? The exit base indicator is an exit. It's a width exit that can be represented by formula HIN. IN, which means the indicator part. So when you got an IN, it's not a real formula. The equation for the dissociation is indeed ionization, right? It's shown below. Under certain conditions, at equilibrium, the solution of HIN is just yellow. Okay, yellow, red here. So what will happen to this? What would be the effect of the color of the solution in 5 drops of NaOH are added? 5 drops. So remember, what you just see it, right? At equilibrium already, it is a solution as a yellow color. So what will happen if I add a few more drops of alkaline into it? So what will be the answer? Someone say A, right? B, C, or D? It's originally yellow, right? What will happen if I put it in alkaline medium? Yes, the equilibrium system will be shifted to the right-hand side, right? Because hydroxide will destroy, will react with hydrogen ion, will make this one concentration drop. The equilibrium position will be shifted to the right-hand side to compensate the loss of hydrogen ion. So which means that this one, they will at the same time will be in more, right? In the amount. Original color is yellow, final color is yellow. So what will be the answer? It's still yellow. Yellow and yellow. Can you get it? Yes, that's right. This is A. So indeed, if you talk about acid base indicator, now it's not just a question, but also in reality, the real situation. Now for this one, it is acid base, acid alkaline indicator. Most of them, they are weak acid. It's a type of weak acid. While they will have got 2 color form inside that. So if you want to study more about the equilibrium, what is that? It is what we call it as acid-base equilibrium. Another type of equilibrium. So to relate the use of indicator, why some indicator they will change the color in different pH. Just like phenolphthalein, right? You know that phenolphthalein will change the color in alkaline medium, with orange will change its color in slightly acidic medium, right? Why? Because they both of them, they are weak acid, but whether or not they will be ionized to the salt form, they will be much affected by the pH. Now, both of them, that HIN, the equilibriums, this one, they will have different Kc value. So they will have different working range of indicator. Poor. Mr. Chin, you just tell me something new. No, it is an integration of chemical equilibrium and acid and alkali. We call that integrated approach. Do you feel better? Do you feel how beautiful it is when you study chemistry? You finally, topic is not just a isolated topic. You can merge the two. Cyrus, you feel better? Once you can merge it, which means that you can study less. The answer is A. Question 6. Yes, the statement incorrect. A is not correct. Why? This is the sentence, right? No change. This one, it will be changed by temperature. Okay? Yes, that's right. Good. Finally, you can catch up. Congratulations. You have successfully got into the space shuttle. Congratulations, Cyrus. How about question 7? Consider the following chemical equilibrium system. This one, N2 plus O2 to form NO. Increasing the pressure of a system will lead to, yes, they will both increase the rate but not affect. Now, increase the rate. What is meant by the rate of the reaction? Rate refers to what? Forward rate or backward rate? What is meant by increase the rate? Increase the rate with what rate? Forward rate or backward rate? Zhu Junfei, you know it? What does mean by rate? Yes, both forward and backward rates. So remember, I need to add one more term to the same extent. So that's why, to the same extent. So that's why you may see that doesn't affect the equilibrium position. And one more thing you can check is the total number of stoichiometry is 2 mole on product of reactant. Here comes 2 mole of product. Okay. So once I write down the QC value, it is independent of the number of volume of the container. Right? You know that the volume terms has all been cancelled out. So the answer is D. Are you with me now? All of you, could you feel better? Now the final 2 questions on the long questions. Sorry for having a very long lesson today. Today morning, especially in the morning. Question 22. Question 22. The equilibrium, this one, it is the past paper question. In that, it is acid-base indicator, right? Can you see that? 4-nitrophenol is colorless, but 4-nitrophenoxide ion is yellow. What's mean by phenoxide? Phenoxide refers to here. The salt of phenol. Phenol, what is that? Phenol is this. This is phenol. Phenol. Okay, phenolphthalein, phenol here, which we have got that part. We got the phenol. So it is a type of acid-base indicator. It will have different color, right? The KZ expression, it is 8.0 times 10 to the power minus 6 mole per dm cube. Can you see that? Why is it mole per dm cube? Right? These two terms over this term, right, equals mole per dm cube. How about right expression for Kc? You may use HA to represent this one and this one. Yes, that's right. Good. Perfect. So you may give a very simple expression. How? Kc equals what? Hydrogen ion concentration A minus ion over what? HA. You know, to represent all those above, right? This one is HA, A minus, H plus, right? Correct, right? It's easy, right? How about this? And right, about ionization attains equilibrium at 25 degrees. The pH, yes, that's right. You have to go back to calculations in acid base. Yes, you are going to find out hydrogen ion concentration, right? You calculate the ratio of the concentration of this. This is what? Ratio of this to concentration of this ion. So what is meant by that? Concentration, ratio in concentration of these to this in this solution. So which means the concentration of HA, okay, over concentration of A minus. So you have to calculate this according to the question, right? Ratio of this. Can you get the point? Ratio of this. Now, good. You are going to change this one to hydrogen ion concentration. 10 to the power minus 2.4, which is 4.0 times 10 to the power minus 3 mole per dm cube. Okay, so you use this data for further calculations to calculate this. How? So you put this Kc value into the calculations, right? Kc is equal to, can you get my point? 4.0 times to the power minus 3 times hydrogen A minus concentration over HA concentration equals 8.0 times 10 to the power minus 8. You flip over the terms, okay? You exchange all those. So what you will get is HA concentration over A minus concentration is equal to, yes, you flip over. These two unknown terms, you flip it on the right-hand side and do it in the reverse. So it is 4.0 4.0 times 10 to the power minus 3 over what? 8.0 times 10 to the power minus 8. Can you get the point? Can you get the point? So finally, what is that? You have to make it our simpler terms. What is that? Which is about 5,000 to 1, right? The ratio. 50, sorry, it's not 5,000, it's 50,000. 50,000 to 1. So what is the hidden message of this? Mainly at acidic medium, which one is more dominant? Which means that at pH equals 2.4, which one is the dominant species, right? HA concentration will be over 1. So that's why I mark it as 2 larger than arrow, right? Much larger than A minus ion, which means that the colorless solution can be found, right? Because this one dominates. So the solution, it is mainly colorless, unless yellow species here, too little to be seen. Okay, so you may still see the solution being colorless. So this is the question B. You talk about that question B. So remember that was the very important item for you to judge. C, suggest is that any color change when any which is added gradually to the solution B, explain your answer. So originally it is yellow, it's colorless. So what will happen? The once I add more NaOH, add NaOH, so what will happen to the disruption of the equilibrium system? There will be change, right? And NaOH will lead to what? Will consume hydrogen ions, right? So once I consume hydrogen ions, what will happen? Hydrogen ion concentration will drop. So what will happen? Do the equilibrium system will respond? Yes, that's right. So the more hydrogen iodide HA will be, yes, you may see the Q0 then Kc equilibrium shifted to the right. Yes, that's right. You may use this way. What else? If I have this one, it will lead to what? The backward. You may also use this way. The backward rate will drop. All right? The backward rate will drop, which will make the forward rate the same. So the net will experience a net forward reaction. They will lead to a net forward reaction. So what is meant by that? The equilibrium position will be shifted to right-hand side. So it is not the end. Now, because it's just the explanation, part of the explanation, part of it. So you have to write more on the relationship on the color change, right? You need to relate to the color change. As this one, you may use this one, right? So you may have the HA, you know that it is colorless, while for A minus is yellow. They will make this ratio, what will happen? So this ratio to become larger or smaller? Right, this one will decrease, or this one will increase, right? The whole thing will drop, right? The whole thing will drop, which means that the solution, there were changes from colorless to yellow. So you use this to explain the color change. Can you get the point? If you don't love that relationship, don't worry. What you just focusing on is on this part. If you don't understand this way, if you don't understand this, don't worry. What I'm going to tell is very simple. So after the shifting equilibrium to the right-hand side, what will happen? The concentration right-hand side, this one will drop. This one will increase, right? So you may find that the hydrogen HA, the concentration will drop, but at the same time, this one, IA minus, will increase. But remember, match the color. The colorless solution will drop in concentration, while this one, yellow, will increase. So that's why the solution changes from colorless to yellow. Do you understand? So you need to explain that very, very well using this type of saying. Suggest one possible use of 4-phenol, nitrophenol, and acid-base titration experiment. So you know what's that? It is used as a acid-base indicator to detect to detect the endpoint, to show the endpoint of the titration. Can you get my point? So acid-base indicator show the endpoint of the titration. To show the endpoint. Questions? Questions? Question 23, last one. Something about organic chemistry. The ester is commonly known as dimethyl malonate, DEM, occurs in the strawberry and the grapes. It will have a acid A according to the following equilibrium. So what is the IUPAC name of this acid A? Huh? What is that? What is that? Suddenly go back to okay. A. Methane diol acid. Agree? Agree? Cyrus, do you still remember anything about OChem? How about another Cyrus? Gone away. Samson. Hey, wait a minute, Chen Weiho is not here. Ah. Samson, tell me. Do you still remember how to name that? What is mean by methane? Methane, which means one carbon. How many carbons are there in the molecule? 3. The answer is not methane dioxide. It's propane dioxide. Yes, that's right, with an E here. Great. Perfect. Propane dioxide. So remember, okay? We've got an E here. Propane dioxide. How about B? Concentration, the equilibrium constant for the reaction. Calculate. The mixture, mixture of 2.40 mole and 9.60 mole were left to reach equilibrium, and the small amount of conc acid. Equilibrium mixture contains this one of DEM. Oh, that's right. Oh, I know. At equilibrium. This one is at equilibrium. It's just 1.60 mole. This one is just initial. So what you're going to do is to calculate the equilibrium constant. So even though volume is not given, it just give you a V here, right? So you still get the answer. Why? You may still get the answer. Why? Do you know? So the initial, to get to know initial, it is 0. Initial is 0. How about at equilibrium? Equilibrium, we have got 1.60 mole. You've got an increase in 1.60 mole, which means that these two will have got a what? A drop on what amount? Is it both of them 1.60? No. This one is 2, right? So we have got a drop of 1.60 mole for the exit. How about this? They will have a drop of 3.20 mole. Can you get the point? So in order to get to know the equilibrium moles, so which means it is 0.80 mole. How about this? 6.40 mole. And here comes 1.60 mole. So you use these three data to calculate. Okay, you use these three data to calculate. So the Kc, it is equal to what? You have to get to know this. It is DEM concentration are O times H2O concentration square. Okay, over A concentration times the alcohol C2H5OH square. And then you need to cancel out all those. Even though I've got volume terms, don't worry, all those will be cancelled out. Okay, 1.60 over V times this one, 3.20 over V square over A, it drops to 0.80 volume times 6.40 over volume square. So all those V will be cancelled out. So here comes the answer, 0.50. Because of that, tell me the unit. No unit. Perfect, no unit. It's just 0.50. But you have to show it V clearly, right? Because for the equilibrium, the total volume is V dm curve. So anyway, even though you know you finally you can cancel out, right? You still write it down from these to this, right? To show the V here, and suddenly the V cancel out. I know it's a little bit clumsy, but you still need to, because the question asks for you showing V here, right? Just show it and tell me all those V they are put here, and all those can be cancelled out, and that's it. Okay, the total volume of the mixture was double, and the addition of more of the inner solvent, which means not reactive, unreactive. It's just used as a solvent, right? But not take part in the chemical reaction. State and explain. Now remember, state and explain, you need to do two things. The effect of this addition of the equilibrium yield of DEM. What is the effect? The answer is no effect. Why?
因為個 Kc 淨係會被溫度影響。
因為 Kc 值受溫度影響。What else? No, equilibrium yield is not just shown as by Kc value, but also the shifting in position of equilibrium. Can you get my point? So even though the Kc value doesn't change, in case there is a shifting in equilibrium position, the equilibrium yield will also be changed. Okay, so it's not good try, but you have to relate something more to the. Yes, Kc doesn't change, but anyway, equilibrium yield refers to what? It's not just refer to Kc. It's refer to shifting in equilibrium position, right? Right? It's not so direct only with link between the two. Okay? So which means that the equilibrium yield can be related by the shifting equilibrium position, while the shifting equilibrium position can be achieved by what? Change in Kc value. So you know that temperature will play a role. How about this? You may need to change what? To change the concentration or pressure. Just go back to the question. Do you understand? The relationship between the change in equilibrium yield will be this. Do you understand? The two factors. But the three mean that first of all, temperature, it will change the value, Kc value, they will change in the equilibrium position. However, concentration or pressure will also be changed, but no change in Kc, they will drop to the shifting equilibrium position. So what will be the answer? So what will happen to Qc? Qc, if I add more solvent to it, increase the volume to it, what happened to the Qc? Yes, Qc doesn't change. The Qc doesn't change upon the addition of solvent. Why? So indeed, the volume here, the volume terms here has been cancelled out. Qc doesn't change. So you have got still have got the equal number of moles of reactant and product of the equation. So upon the change in the inner solvent, so which means that no shifting in position of equilibrium. So no change. Is that clear? I do think it's fair enough for all of you to get to know more about this part. A very long lesson today, just like the normal lesson, nearly a double lesson. So nearly I will stop here. Any questions so far? You feel good? Just give you some warm up, right? For it seems like the normal lesson now. You feel good? Now I would like to check who is absent. Choi Gao-wei, you just entered the classroom. You just enter it. Where were you this morning? Can you show me the list of students who are absent here? 吳晶豪 and 蔡俊明、陳偉豪. Who else is absent? 趙家明、胡家龍. Yuan Tian Yao. Yes, that's right. Who else? Lou Xiaohua. Are you here? Who else? Oh, you are here. It seems you disappear. Read only. Who else? Sorry, sense of existence equals 0. Sense of existence, 0. Who else? Lý Dân傑 here, 余子豪、梁善維、李彤 is here. 魏卓賢、龐家豪 came to. 徐家榮袁. Who else? I've just pointed 4. 16, that should be 16. 15, it's 19. 3 more. 3 more students absent. Could you please help? They will be either class A or class B. Lê Yinon is here. And is Lê Yinon here? Yeah, here. Who else? Class A and B. Could you please find out your neighbors to see whether or not they are here? Now, anyway, I just kept the screen and then I'll let you check by my own later. How about the others? Could somebody who still haven't told me your level of understanding from 0 to 10? Do it now. It's not just letting me know, but also let you yourself know. Again, you just show me 7. Are you sure you just have you watched the video on the previous 2 lesson? You better watch it. Great, great. So it's time I expect you guys to come back every night. Okay? Can you manage to come tonight? You just say yes, okay? I will just treat the yes here for my question. All right. See you guys. Have a good break. Okay. See you guys tonight. Time for temperature. How temperature affect position of equilibrium. Bye bye.